Alright, last time we were looking at that review lesson from chapter 1 on logs, solving log equations. We looked at changing the form, logging both sides, one-to-one property of logs. All that's in the notes from last time. So let's look at just a few more little examples out of this, 5 or 10 more minutes worth, and then we'll go back over to chapter 3 and work on our derivatives. Now let's say we have log of 1,000. Type that into your calculator and see what you get. Three. Okay, the calculator tells us 3 because anytime you press the log key, you've got an understood base of 10. So you're saying 10 to what power makes 1,000? So that makes sense, doesn't it? I raise 10 to the third power. 10 times 10 is 100 times 10 is 1,000. So then without the calculator, what would log of 100 be? 2. 10 squared would be 100. What about log of just a 10? 1, right? 10. All these are common logs, right? 10 to the first would be 10. So this is another one of those White House rules where you've got a base of 10, you've got a number of 10, so the answer is the exponent, which is the 1. All right, log of 1, 10 to what would make 1? 0. So that's one just to remember. You probably remember it from pre-cal. Log of 1 is 0. A log of 0. 10 to what power would give us 0? Doesn't have an answer, does it? So if we did 10 to the 0, that would give us this one, wouldn't it? That would give us our 1. So this one is undefined. Log of 0 is undefined. Can't raise 10 to a power to give us 0. What about log of, say, negative 10? Any negative number. 10. Even if we raise 10 to a negative exponent, that's not going to give me a negative number, is it? This base raised to a negative power, we'll just put it on the bottom, but it would stay positive, right? So if I raise 10 to the 0, I get 1. If I raise 10 to something positive, I get something positive. If I raise 10 to something negative, even if I use that, that's not negative 10, is it? 10 to the negative 1 is what? 1/10, right? So the log of something negative is also undefined. Now, there may be some solutions that are imaginary. Your calculator, if you type in the second one, might say no real roots or no real solution. Maybe there is an imaginary solution, but we're only interested in the real ones. All right, now this next little part of the notes is a skill that's going to help you a lot, maybe more so in Cal 2 if you take Calculus 2 than in here, but I'm going to go ahead and show it to you. Anytime you have e or some number raised to a power that has logs up in the exponent, if that exponent has a coefficient on the log, 3 ln of 7, 8 ln of 7, 9 ln of 7, anything but just an ln of 7, then before you can treat this like one of the White House problems, you've got to take that coefficient, move it up into the exponent. So when I move that up, I get e to the ln of 7 cubed. So that base and that number are the same, and I've got a 1 in front of my ln. So when those match, and there's a 1 here, my answer is whatever's left over, which is this. So 7 cubed, or what 7 times 7 times 7? 49 times 7 is how much? You're going to calculate and say 7 cubed. In case the book would want a numerical answer. 343, okay. So that shows up a lot in word problems coming up later on in a few chapters from now. Okay, in the last little part of the notes, we might say section 1.5, Two problems. Simplify. Number 16 over on the homework page for 1.5. Without your calculator, simplifying 13 raised to the square root of 2 raised to the square root of 2 over 2. All right, 13 to the square root of 2, I'm going to put a 1 on bottom. Anytime I've got a power to a power, I multiply my powers. If I had 7 squared to the 5th, that's 7 to the 10th. That raised to that times that is going to give me my new power. So the square root of 2 times the square root of 2 is the square root of 4, which is 2. And then 1 times 2 is a regular 2. And that reduces, right? So my final answer is 13. Okay, you try this one. Last one on this lesson. Square root of 6/3 squared. Okay, square root of 6 times itself makes what? 6, right? And then 3 squared, 3 or 9? 9. It's not under a radical like the 6 says, so we've got to square it, and it's going to change appearance. So when we reduce that down, what do we get? 2/3, right? So your 1.5 assignment that I didn't turn on, I think I turned it back off after Wednesday's notes because we didn't get that far. I think it only has 3 problems. 3 homework, maybe 3 quiz questions. So that's not going to take long. All right, any questions about anything you've seen so far on 1.5 or 1.6? Okay, let's go back over then to chapter 3. 3.8. Derivatives of logarithmic functions, page 176. If we made a list of all the different types of functions we know how to find the derivative of so far, we would have e's on our list. But e's aren't logs, are they? Like that problem on the board I just worked, number 15, it had an e to the 2x, so we knew how to find its derivative. Sine, derivative of sine is cosine. So all 6 of the trig functions, we're all right with those, aren't we? Polynomials. Group 3 had a problem that had 1, 2, 3, 4 different little polynomials, and they found the derivative of each one, right? So we're okay with polynomials. We're okay with products, product rule. We're okay with quotients. You know, we know how to find the derivative of a lot of different kinds of things, but we don't know how to find the derivative of log functions yet. That one's not on our list. So that's what this lesson's about. That's why we went back to chapter 1 and reviewed for a while there on just how these problems work before we find their derivatives. Okay, our first column, I'm going to call it the function, and the second column is going to be the inverse function. Back in pre-cal math 112, if you had a function, a lot of times you'd call it f of x. And then if you had its inverse, you would call it f inverse, or the inverse of f. And we put that little -1 up there to name it, to show that it's the inverse. Didn't mean to move it to the bottom and make it 1 over f, did it? It meant inverse. And there were about 5 or 6 steps you'd go through in chapter 2 in math 112 to find the inverse of a function. You'd have to be sure it was a 1-to-1 function, and then you'd have to rewrite f of x as y, switch x and y, solve for y, change y back into f inverse, and then check the domain and range to see if those matched up. So there were a good bit many little steps there. Just remember in the notations what I want us to see here. So let's say we've got this e function. You know, one of the things that we know how to find the derivative of. If that's the function, then the inverse function is ln of x. So really what I did here was I changed the form. I switched places and I changed the form. So instead of it being in exponential form, now it's in log form. So the exponential functions and the log functions are inverses of each other. They're inverses of one another. Put a big star by this. Very important. The derivative of ln of x. The derivative of ln of x is 1 over x times the derivative of the inside. What's the derivative of just plain old x with respect to x? It's just a 1, isn't it? So the derivative of ln of x with respect to x is 1 over x. So the derivative of ln of something is 1 over that stuff, 1 over whatever it is unchanged, times the derivative of the stuff. Now here's the better form of this, because this next one covers any kind of stuff you might have in there for x. The book calls it u because it might not be nice, perfect little x. It might be 2x, like that problem on the board, or it might be 8x squared plus 5x minus 7. It's just more than an x. So to find the derivative, though, of ln of something, I put 1 over that stuff. I don't care how complicated the stuff is, I don't change it. I put 1 over it. Times, and then I go inside, and the derivative of the actual thing is what I attach here at the end. So the derivative of u would be du, and I found its derivative with respect to x. So both of those are important. The second one, though, is probably more practical. Now, for homework, I want you to read the bottom half of page 178. For the why, the derivative of ln of x is 1 over x times 1. The derivative of ln of u is 1 over u du dx. I'll give you the steps there in your book. What I want us to do right now is to practice together how to find some of these derivatives. So let's try this one. Example 3 on page 179. The derivative of ln of 2x with respect to x. Okay, it's an ln problem. It's not itself. What the derivative of what is itself? From the board over here. It's derivative of what kind of function? E, right? Derivative of e is itself times the derivative of its exponent. The derivative of ln of something is not itself. You can't say, well, it's itself times a 2, because the derivative of that's a 2. No. You can't get e's and ln's mixed up. Okay? What do we say about e's and ln's? They're inverses, right? If you've got this kind of problem, the derivative of it's different from the derivative of this kind of problem. Sometimes students forget which one they're working with. We're doing these today, right? ln's. Okay, so the derivative of ln of something is 1 over this thing. 1 over 2x. 1 over this stuff, none unchanged, times the derivative of the inside. So the derivative of 2x is 2. And then, sometimes I can simplify, sometimes I can't. Here I can. Since these are multiplied, I can reduce those. That gives me 1 over x. Alright, I want you to try this part without looking at the book solution. Find the derivative of ln of x squared plus 3. Well, you should have gotten 1 over x squared plus 3. Be sure you didn't put an ln down there with it. Just 1 over this stuff times the derivative of the inside, which is 2x plus 0, so a 2x. I can't cancel here because this is added, got an added 3 with it. It's not multiplied like it was up here totally. We've got that, right? So we're just going to have to leave it. 2x times 1, 2x over x squared plus 3. How many of you got that one right? Or you were on the right track? Okay, any questions about B part? Again, don't put an ln down here with it. It's 1 over this stuff, not 1 over the whole problem. There's no ln down here on the bottom. Now let's make a little chart in our notes. Let's write old and new. Alright, first old problem. The derivative of e raised to the power of u. Derivative of e to the u dx. That u just represents something complicated, possibly. It could just be x, but it might be more than that. So we've said the derivative of e to the u is e to the u. It's just itself. Times what? The derivative of what? It's inside, right, which is the u. So times du dx. Itself times the derivative of its power. So on the board, that would be the e to the 2x, would be that part, and then that would be the 2. Looking at that number 15. Okay, so that's an old problem. Very important that we know that. New problem. The derivative of ln of u with respect to x. It's a log problem. It's an ln problem. So how does it start out? Good. 1 over u times du dx, right? 1 over the thing times the derivative of the inside. So the du dx is the same for both formulas, isn't it? That represents the derivative of the inside. That represents the derivative of the inside. So that one's very important. So you need to learn those two. Both of those. Okay, now the next two are going to be given formulas. I'll give them to you and then you decide when to use them and how to use them. You'd probably be better off just to memorize them because most students have the worst time with these two formulas, and I think it's because I don't require anybody to memorize them. So maybe I need to change my policy and say, okay, everybody's got to memorize these two. All right, what if you had something besides e raised to a power? What if you had, say, 7 raised to some power? That a represents a constant, okay? A represents a constant. All right, the formula for that is a lot like the formula for e to a power, because isn't e a number? What is e as a decimal? About how much? 2.7 something, right? 2.71828. So if that's a 7, it's still a number, just like e is. All right, here's how it starts out. It would be itself, just like e was itself, but it's times the log of the exponent. No, times the log of the base. Ahead of myself. Times the log of the base times the derivative of the exponent. So the first part matches the formula you've got to know. The last part matches it. The only new part is this ln of a. Well, if that's a 7, then I would have an ln of 7 right here. Now up here, if you wanted to, you could squeeze in an ln of the base, but it would be an ln of e, and ln of e, we've already said, equals 1. So that's why we don't write it here. So technically, they're exactly the same formulas. ln of e equals 1, so we don't bother with writing it. Now let's do an example of this one before we go over here to this next column. Let's see here. Number 68. Y equals 3 to the negative x. So the problem says find the derivative. All right, the derivative of y is 1, but y is not x, so what would we attach? 2y dx. Here I've got a number raised to a variable. This is an example of this problem here. A is like my 3, okay? So it's going to be itself times ln of the base. What's my base this time? 3. Times the derivative of the exponent. Derivative of negative x is negative 1. And that's my answer. Now I just got to rearrange a little bit to make it look a little better. So let's put the negative ln of 3 out front. And then times a 3 to the negative x. Okay, so if you're given that formula, you should be able to come up with that answer. Even without the formula, you might be fine with working it. All right, now then let's go over here to our next column, which is another given formula. Instead of ln of something, what if we have log? Derivative of log base a of u with respect to x. It might be a base 10. It might be a base 7. It might be a base 746.8. It's just something besides, what was it up here? Invisible base of e, right? Natural logs have a base of e, so we're talking about some log problem that doesn't have a base of e. All right, it kind of works like this one did. When you find the derivative of ln of something, you put 1 over the stuff, don't you? So right here, we'd put 1 over u. Just like we did up here. Here's the new part. On the bottom, we got to say times ln of the base. The base is a. ln of a. That's a 7. I got a ln of 7 right here. Times du dx. Times the derivative of the thing. So that matches as well. So this is the only new part, just like this was the only new part over here. And again, up here you could do that. You could squeeze in on bottom an ln of e, but it would equal what? ln of e is 1, so you really just don't write it, but it's there. So these are the exact same formulas. We just use these ln's and e's so much more than these two. That's going to make these a little harder. When you ask how to do it, I'm going to say, well, it's one of those given formulas. Let's see if I've got a good example of that one. Let's do number 74 as an example of this one. Find the derivative of log base 3. Okay, red flags, right? Going flashing because we know we've got something besides an ln problem. It's a base 3 log. Theta ln of 3. Okay, so the derivative of y is 1. dy d theta. So we've got thetas instead of x's this time. Equals. If it were ln, wouldn't I put 1 over the stuff? So I'm going to put 1 over my stuff. My stuff is 1 plus theta log of 3. That's the u here, that's the jump. Times log of the base. Base is 3. Times the derivative of the inside. What's the derivative of the inside? 0 plus, what if that were x? X log of 3 would have a derivative of 1 times log of 3. It's weird because the number's at the end, isn't it? 1 plus theta log of 3. Log of 3 is a number, so it'd look better to maybe have log of 3 and then your theta away from it. So the derivative of theta is going to be 1. So 1 times log of 3 is log of 3. Derivative of a constant is 0. So 1 times log of 3. So the derivative of the inside part here is a log of 3. It's here at the end. I don't have room to squeeze it in very well. All right, now that one's going to cancel with that one because that one's a multiplied log of 3 on bottom. Now there's no way I could cancel it with this one in here because it's added to a 1. So what's left is a 1 on top and a 1 plus theta log of 3 on bottom. So these two you need to know without the formula being given. These two the formula is given, but realize they're the same formulas as those. Just got an extra little log of the base that's got to go somewhere. Here's how I remember it. If you're finding the derivative of a variable, if you're finding the derivative of a constant raised to a variable, you write itself, and the log goes right beside it. Over here, the derivative of the log is 1 over something, and the log of the base goes right beside it. So you're putting that log of that number right beside the first thing you wrote down. Here it's on the top, here it's on the bottom. Here it was itself, it went on top. Here it was 1 over the stuff, it went on bottom with the stuff, right? So if that helps you remember where they go, even though they're given, it might help you tie it into these old formulas and make it a little bit easier. Now then, let's look at an example of why the derivative of log of x is 1 over x. Show that the derivative of ln of x is 1 over x. And they tell us that x is positive. It's because we don't want to find the derivative. We don't want an ln of a negative or a 0. It's what happened earlier when we tried to find ln of zeros and negatives. Define, right? So we're just keeping it real, right? Like Randy Jackson on American Idol. We're keeping it real. We'll keep our x positive, so we have a real number here. Now, a lot of times when we don't know the derivative, we go back to the formula for the derivative, like, limit of f of x plus h minus f of x. But we're not going to do that this time. To show it, we're going to do it another way. It's a much easier way. I want you to change the form on this. ln of x is the function that they give us to work with. Y is equal to that. That's always y, whatever you see there. So take y equals ln of x and rewrite that problem. Okay, what did you use for the base? Invisible what? Right there. E, right. E raised to the y power equals ln of x. Equals x. E raised to the y equals x. So that's what we did last Wednesday. That was the 1.6 notes from chapter 1. All right, I've changed the form. And you're thinking, what are you supposed to do with this 1 over x? Nothing. That's supposed to be the answer. We're going to work with this side and see if we can come up with this side. Now, when we change the form, we've turned it into a problem that doesn't have any ln's. So don't we know how to find the derivative of e's? We can't use our formula for the derivative of ln if that's what we're trying to show right here. We're saying we don't know what the rules are when we're given this problem, so we're trying to work it some other way. So we rewrite it, we can do it the some other way, which is old lesson, right? Derivative of e is itself times the derivative of its exponent. What's the derivative of y? Right, just a 1 dy dx. Because y is not x, right? And then the derivative of x is 1. All right, now we've got to get dy dx by itself. That's what we're solving for. So we're going to divide both sides by e to the y. So those are going to cancel. So now I've solved for the thing I'm looking for. So dy dx is 1 over e to the y. You're saying, well, that doesn't look like 1 over x to me. I thought we were supposed to get 1 over x. What does e to the y equal? X. So can I substitute that in? Take it out and replace it with x? Because right here we said they're equal, didn't we? Okay, so we got what we said we were supposed to get. So we just proved that when you take the derivative of ln of x, it's 1 over x. Times the derivative of x here was a 1, so I didn't have any extra stuff to attach at the end. But again, if that's a mess, then you attach the derivative of the inside to the end. That's the chain rule. All right, now let's test our calculators and see how many decimal places our calculator gives us e to. See if your calculator chops it off or rounds it up or only gives you 2 or 3 decimal places. If it only gives you 2 or 3, you need to reset it so it'll give you a whole lot more. So type in second log to get e to the first power. It may not quite go that far. It may stop somewhere along in here. But if it's only giving you like 2 or 3 decimals, go into mode and reset it to give you the most decimals it'll let you choose. 1, 2, 3, 4, 5, 6, 7, 8. Mine's giving me 9 decimal places. How many of yours went out that far? At least 9. Okay, good. All right, so we just saw what the number e is in calculus. It's about 2.718, on and on and on. So the number e is very useful in calculus. It's a very useful number. So make a little note to read page 37 to the middle of page 38 for homework. And your book goes into a good bit of discussion on why it's such an important number. Now, if you look at the bottom of page 37, right below where I want you to read to for homework, bottom of page 37 in bold print, the graph of y equals e to the x has a slope of 1 when it crosses the y-axis. The graph of y equals e to the x has a slope of 1 when it crosses the y-axis. Okay, look at those graphs in your book. You've got y equals 2 to the x. Isn't 2 a little bit less than e? E was 2.71828. Line, your slope is 0.7. Here your base, your slope line at 1. Here your base is a little bit, so the sign at the y-intercept is 1.1 about. So the slope of that tangent line being 1 when the base is e is what makes calculations with e. Definition. This is e without e. You know, a minute ago I calculated 1/8 to 8 or 9 or 10 decimal places. So if you let, now this is not a wavy equal sign either, this is exactly e. So if you let x get larger and larger and larger and go to infinity, let this get larger, and you keep typing in your calculator, you're going to approach e. That's the true definition of e. Now another way to write e, I don't know that this one's in your book. If it is, I didn't find it. But a lot of books will write e this way. Instead of the 1 over x being here, they call this x and they make their exponent 1 over x. And if they do that, then x has to approach 0. That's the same thing. That will also give you 2.71828. Either one of those is exactly e. No rounding. All right, let's look at a couple of little exponent problems, and then we'll go back to logs. Derivative of x to the square root of 2. Square root of 2 is a number. If that were x squared, nobody would panic and say, oh, I don't know. It doesn't, it looks different now. It's thinking, oh, what am I going to do? I'm going to do the same thing you'd do if you were in group 3 and you took the derivative of x to the 4th. What did they get? 4x cubed. The derivative of x to the square root of 2 is what? Bring that down. What do we get?
Square root of 2x to the square root of 2 minus 1.
Exactly right. Bring the power down. Subtract 1. We can't beautify that any more than we got it unless we turn it into decimals, and then we'd lose some of our numbers. So we're just going to leave it like that. Bring it down, subtract 1. All right, B part, the derivative of 2 plus the sine of 3x to the pi power. Got a bunch of stuff raised to a number. Say, I don't know what I'm going to do. That's a pi. Pi's a number. Pretend it's a number. Do the same thing. Bring the power down. It's a number. It's not a variable, is it? 2 plus sine of 3x. Subtract 1. Go inside. Derivative of constant 0. The derivative of sine is cosine. A lot of students will do that. They'll say cosine of x because this teacher wrote it on the board and said we're having a quiz on it. It's cosine of your thing. Your thing is 3x. So that's, if you write x there, you missed it, didn't you? Cosine of the thing, the angle that you have in your problem, times the derivative of the sneaky inside. Because a lot of students say, I don't see an inside. This stuff right here is inside. Now you got an inside the inside, don't you? Because this is the angle and it's more than x. So what's its derivative? 3. It's good practice for the test today, isn't it? So the derivative of the outside, bring that down, leave everything just like it is, subtract 1, times the derivative of the inside, 0 plus cosine of 3x times a 3. All right, now then, I can't do a whole lot of rearranging, but we could bring the 3 out here because it's multiplied, and we could bring that out too, I guess. So 3 pi cosine of 3x times 2 plus sine of 3x to the pi minus 1. Or some other order that you like better would be okay. Any questions about those two exponent problems? We'll go back to logs. Okay, now here's where our old chapter 1 really starts to come into play. So take a deep breath, look at your neighbor, keep a close check on them during the next example, have your smelling salts on standby. If they look like they're getting ready to pass out, and shake them and wake them up. Example 6, find dy dx. And the book says use logarithmic differentiation. All right, the good news and the bad news. Let's do the good news first. The good news is that it's solved for y. Y is on one side by itself. The bad news is the other side's a mess. But we've seen messes before, haven't we? Kind of like the chain rule. If you leave the problem written just like it is here, and you tried to find the derivative of this side, you'd use the quotient rule. So you'd do the bottom times, and then when you got ready to do the derivative of the top, you'd have to do the product rule, wouldn't you? Because it's stuff times stuff. And when you're doing the product rule, you'd be using the chain rule because these are kind of a mess, aren't they? So it would be ho d high, and d high would be the product rule and the chain rule, minus high d ho over ho ho. So you could do it with it written just like it is here, but it would be a whole lot more work than the way we're about to do it. All right, the book says use logarithmic differentiation. All that means is log both sides first, then rewrite. Let's say then split up. Now, so what we're doing right now is not calculus. What I'm doing right now on this first step under solution is chapter 1, like your 1.6 homework that was due today. So I'm going to log both sides. So we're going to use LNs because we saw in our formulas how LNs are easier to work with than LOGs. You could use LOGs, but we're going to make it simple. So we're going to LN both sides. I'm not changing anything other than writing an LN in front of both sides. And sometimes you had to log both sides to solve those old chapter 1 equations. So when I log this side, really there's not much over here to work with. When I log this side, I've got the log of something times something divided by something. So I'm going to use rules 1 and 2 of logs to split it up. Okay, rule 1 of logs. If the numbers are multiplied, the logs are, what are we going to do, add or subtract? Add, right. Ln of the first factor plus Ln of the second factor. And we got some divided stuff, so we got to subtract minus Ln of the bottom. If we had some more stuff on bottom, we'd say minus another Ln, wouldn't we? Minus another one, minus another one. We had 4 or 5 factors on bottom, minus log of every one of them. All right, now we're going to use rule 3 of logs to move this exponent down front, this 1/2. Because if we forget, it gets kind of ugly, so don't forget. You'll probably only forget once. After you forget once and see how bad it can be, so I don't want to ever forget to do that again. Now this exponent can't be moved down because see how it's inside the parentheses, so we're going to leave it where it is. So now we've got Ln of y equals Ln of this stuff plus a 1/2 Ln of this stuff minus Ln of this stuff. So we still haven't done any calculus, but we've separated all of our junk on the right side and made it into 1, 2, 3 separate little log terms. Right, now we're going to find the derivative of all 4 of our terms. 1, 2, 3, 4. And every one of them are log terms. So let's go back to our notes. So when you find the derivative of Ln of something, you put 1 over the stuff times the derivative of the inside. We're going to do that 4 times. So we got 4 log terms, right? We're using this important must-memorize formula. All right, so here we go. The derivative of Ln of y is 1 over the stuff times the derivative of the inside. And the derivative of y is 1, but it's not x. So what do? dy dx, right? You can't just say dy dx equals, because that's what it said to find. It said to find that, so I'm going to write dy dx equals. You've got to find the derivative of Ln of y. 1 over the thing times the derivative of the inside. All right, next term. None of these have y's, so we don't have to worry about any dy dx's anywhere. But it's an Ln problem, so I've got to put 1 over x squared plus 1 times the derivative of x squared plus 1, which is 2x. Plus the 1/2, we just ignore it, it's a constant coefficient. It's just up in the bleachers watching the game, right? And the derivative of the Ln of this junk is 1 over that junk times the derivative of x plus 3, which is 1. Okay, what about the last term? What's it going to look like? Minus what? Good. 1 over x minus 1 times the derivative of x minus 1 is 1. Okay, that's the only calculus in the problem. Anybody want me to go back through that step or parts of it? So by logging both sides and splitting all that junk up, I avoided the quotient rule, the product rule, and the chain rule, really, as far as the chain rule in the middle of a product rule. All right, now I got 1 over y dy dx equals 2x times 1 is 2x over x squared plus 1. You cannot cancel. For the same reason up there on the board, I didn't cancel my cosines. I had 2 terms on top and 1 on bottom. Here I've got 2 on bottom, 1 on top, but you can't mark out part of that. Right here, 1 times 1 times 1 is 1. 2x plus 3, I'm just going to leave it like this. If you want to make it 2x plus 6, that's fine. Minus 1 times 1 is 1 over x minus 1 times 1 is x minus 1. All right, next step, we've got to get this by itself. So we've got this 1 over y on the left side. Let's flip it and multiply both sides by y over 1. So y times this side is going to cancel it out. Then I got to do y times this side, don't I? I multiply one side by y, I got to multiply the other side by y. So that eliminates the stuff that was with what I'm looking for, which is dy dx. So my answer is y times all of this. But the book wants the answer in terms of x. So at the very end, it's a little simple substitution, but it looks terrible. All they do is change this little y here into what it was in the original problem. This is y, right? U equal your student number. I'm going to take u out, and we're going to put your student number in place of u. So we're going to take out our y, we're going to put in x squared plus 1. X plus 3 to the 1/2. X minus 1. Okay, that's y. All that's y, right? Then we bring the rest of this stuff down. No changes. Students will work one like that and they'll say, where did all that stuff come from? It's the original problem. Thinking, I left a bunch of stuff out, I didn't get any of that. Yeah, you did. You got a y, and that's what it equals. Let's go back and find it in the original problem. All right, now I want you to try number 51 on the homework page for 3.8, and the problem is y equals x squared plus 1 over x plus 1 to the 2/3. I'll give you a hint. You've got to rewrite your radical as a 1/2 power. Starting out. After you do that, it's going to work just like the one we did together. So I'm going to give you a head start. You start on it with your group, and then I'll work behind you on the screen, and you can check your final answer, see, or look it up in the back to see if you got it right. think that's how the book left it. Somebody that checked in the back, is that what it looked like in the back? All right, the x squared plus 1 in the original was to the 1/2, so since it started out as a square root of that on this page, then I'm pretty sure the book's going to go ahead and change it back into a square root here at the end. So log both sides, split up the log of all your products and differences, products and quotients, bring your powers to the front, and then find the derivative of each term. So 1, 2, 3, 4 terms in that one too to find the derivative of. Any part of that one you want me to go back through on 3.8? Any parts you missed and you don't know how you missed it? Okay, then.